Hello everyone. Yeah. It's painful. Anyway, it's me again, Heider. Nice to see you again, and thank you very much for the lovely wishes and the great text and the private messages. Really appreciate it, honestly. Thank you, really, just all I can say. I had as you can see, I'm back trying to fire on 4 cylinders, but you know, it's getting there. I had a problem with the first couple of days. I think I was back in the hospital for about 8 hours, 7.5 hours, in a accident and emergency, or as Yankees call it, the ER section, or the ER. I can't laugh. Yeah. Anyway, yeah, I'm back now. Working on stuff. I did progress a lot on the instrument and did work. I'm like 10 steps ahead from this video. By the way, it's yeah. And what I decided to do, rather than just keep trying to go as far as possible and trying to finish off as much as I can, which kind of blocks the others from seeing what I'm doing, I thought, let me just take a break a bit, rewind a little bit, and go back to something I resolved earlier, just to show you what was the problem and what I've done to resolve it, and just to give you an idea of you know what goes behind the scenes, actually trying to get these structures fixed. And it's quite an important thing, actually, I have to say. If you're Korg watching this, then and you're probably thinking of silly ideas in your head and whatnot. Please note, the functions I am working on are pretty much are the original operating system functions that you'll see in the video, or previous videos or next videos. These are the ones I am working on to reverse engineer, which I'm allowed to do. And also it's the same functions that you provided us with. And you sent this up on the original Kronos DVD that comes with the instrument. So I am allowed to reverse engineer these functions, and these functions are per the GPL license. They should be fine. So anyway, I don't know what else to say. Enjoy. Right, let's just power up things. And that camera should be able to film as well. Yes, I suppose. Hopefully my head is not in the way. Good. Yeah. Oh. So I'm now booting my own original OS, the one I compiled. Okay, I'll try to keep this video as short as possible, even though with these things it's going to be difficult, because I'm probably going to stop the video at some point, and I will either stop it, forward, cut, or probably fast forward, which I like to fast forward usually. Oh god, this is like a plane in here. Fast forward the video to show, because I'm going to recompile the OS now, and then I'll show you the fix and all that kind of stuff. So what makes it difficult on this instrument is because I can't be asked to remove the cover and connect a PS2 keyboard onto the system. I'm now using a USB keyboard connected to this. The problem with USB keyboards is because the debugger they try to disable all the interrupts at the same time. It makes it difficult for the USB not to function as a USB device. So sometimes when I press keys in the debugger, it actually doubles up and triples up and whatnot. And I showed you that in the last video. And sometimes you do get the lockups with the keyboard itself just because of that, because you're trying to put a breakpoint on the key and on the USB function, and the minute you press a key on the USB, the keyboard, it triggers that function and does the breakpoint, and makes the whole thing, you know, problematic. So, but ignore that for now. I've got, you know, as I said, I progressed a lot. Everything is in place, and we'll try to do things in the nicest way possible. So, without further ado, let's just start loading up the modules. Let's do the HAL, the scheduler, the FIFOs, the NDBG, the semaphore, SBIN, STGE, done. So we loaded up the original system, or the original stuff that I was working on from the last video. The issue we had in the last video, and I'll show it to you now, let's just do this. We're trying to run the Omap. That's the same, by the way, the same Omap thing we're doing on the other side, which I did videos on the front. So Omap MKS4 module. So if I run this, see what happens. The system trying to probe it, well, it did go as successful to trying to register the device, but it comes up with the wrong ID set, vendor 2EF and the product 4001. And the problem with this is, as I said in the previous video, it's just to do with the structure mismatch, which makes the cookie cutter of the class go out of sync. So, for example, when you compile the OS, on compilation time, you are telling, for example, that my system variable is X, let's say. And X, when you at compilation time, X will be, when the compiler loads it, X will be, for example, in memory location 1, 2, 3, 4. But when you take this to a different system and try to run it there, X on the other system, because of the different configuration, can be 5, 6, 7, 8. Location 5, 6, 7, 8, which reads something completely different. And this causes the problem. So for example, the cookie cutter that we have for the vendor ID and the product ID is loading up from a certain memory, which doesn't match the one that are actually coming up now. And what we're doing today is kind of finding out, or going as deep as possible to see where this is reading up the variables and can the right variable exist. Now we know previously from the videos that I've recorded, and you probably have, if you have logged into your system to see, you probably know that the Korg vendor ID is 1005 and the product ID is 944 in hex. And if we see those somewhere, then we know, yes, these are the right values, and we need to tell the system to start loading up there instead of here. To do that process is the purpose of this video. And so let's just break into the system. And I'm going to set up breakpoints to break before we load up the module. And we'll take it from there. So, and now I put the breakpoint, and now we're back into the module. So now the kernel is running. If I run the install module again, it will now break, as you can see. Rather than displaying all that shebang to say wrong ID, blah, 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 it's now saying, yes, the module is now ready. We loaded it up in memory. It's ready for you to run. We just needed to if I say go, it will run. But I don't want to do that. So I'm just going to trace into the beginning of the function, or the beginning of the module itself. Now you have the init module up and running. Now the init module is up, and I can see it there. Without going to the module itself, because I don't really care about the module, I'm going to break into the USB registration. So if I do BP USB, yeah, so now I broke into, and now we're running. So the whole thing now, as you can see now, the Omap is saying the Omap MKS4 init line 258, Omap MKS4 init enter. So this is the Omap stuff that whatever it's doing, don't care about that. And now we are at the point that says I am now going to register the driver, and this is the OS again. So if I look into the USB register driver, I can see it down there. And if I look into the variables, I know usually when you pass parameters to the register driver, you need to pass the structure of the whatever you do, and the structure will contain all the information to say, for example, the probe function, the exit function, the disconnect function, whatever function, it's all included in the same structure. The structure usually is based off either pointers or a dissolved kind of other structures into the same structure, makes it bigger. But that's not the this is out of the context of this conversation. So I know we know AX or EAX basically is the pointer to the structure that, or the parameters that goes into the system. So if I look into what AX is, I know this, you can see the first 3 buffers or first 3 32 bits are full, the others are zeros, which, it doesn't matter. I know, because of my experience, I know the second one we're looking at is the probe function that we need to get. So if I would look into that, and if I say, if I put a breakpoint on the probe function itself, so 5a, let me just show you before I break into the thing. So if I do a 5, where is it gone? 5a60, 5017. No, that's not the right one. Sorry. 5a6050. No, that's not the right one. Sorry. As I said, this second variable, I'm looking at the first parameter, so it should be the second one. So MD, beg your pardon, yeah, bear with me. 5A, 5F, that's the right one. CD60. There we go. That is here we go. The probe function is here, which will look into the device or the USB probing and will kind of decide, is this my driver, shall I register it or not? Just a heads up before we carry on with this. In a USB, when you try to register a driver, you would provide the function of the disconnect, the probe and all that kind of stuff, and the probe function will be called instantly, initially, to say, the OS will come and say to you back, yes, I've got this driver that you're looking for. You're looking for the Korg Omap NKS4 driver, and I think I found it. Try this one, have a look. And then the probe function will be triggered. The probe function will look at it and say, yes or no. And this is the thing we are looking at. And this is the thing we'll come in back and say, that's not the right one. I'm not going to do it. I'll register it. This is the wrong function. And now we're looking into this. So if I put a breakpoint on it, we can also do it on text as well. Omap. No, let's just do this. 0x, 5a, 5f, CD60. Right, so now we have the probe at the beginning, and if I run it, and now we're breaking into this again. So now I run the kernel, and now the kernel has gone and brought the USB driver. It kind of talked to the device and then came back and say, yes, is that the right device? And now we can see we're broken up. We're broken now at the probe function itself. So this is the function that will come and say to us, is this the right driver or not? And that's the bit we need to check, or that's the bit we need to work with and understand why is it not doing this. So if I look into the code in here, I can clearly see here on this line, for example, the plus 2D or the 180 here, it says compare EDX with 1005. Now we know 1005 is the one in question, and this is the value we need to read, and I bet you it'll say 2E something, which is not 2005, 1001. And this is gonna get rejected. So usually when the probe is running, it'll pass back to the probe function. The OS will come and say, here is the structure that I needed to look at, and then you tell me if this is the right or wrong driver. Now here, it'll be passed by AX, and then one of the AX pointer, which is 1C, will be pointed at by BX, and then the system will load up BX and say, is this the right one or not? So if I do look into the AX structure over here, right? Now this is the structure that's been passed back by the OS. Okay, this is what the OS is saying to us, that I've got this data, have a look at it. And that structure should contain the stuff you need. So if I start to trace into this, forget EVP, ESV, these are just to push the stack. Push to forget that. Sorry, yeah, so yeah, push EVX, not interested in that, not interested in that. That's the bit we're interested in. And you remember what I said, in location 1C, which is, so that is 10 over here, 1C, it's reading the stuff to say, get the EBX from EAX plus 1C. So now EBX is the one guy we need. And if I do, right, okay. So looking into this structure in here, I hope you guys can see this. If you look at, so we got 10, 20, 30, 40, 50, 60, 70, 80, 90, A0, B0, BC in here. So location plus BC, look, 1005, 0944. That is the device, that is the right device we're looking at. So the USB register function, it's sending to the probe the right information. It is the right device. It's just the Omap is not reading it right, and that's where the problem is. So if we stopped it there, let's just continue browsing this. So now we are loading that 3, forget that, and load effective address, and we're loading into DX, you see that here, EDX plus 11E. So plus 11E, let's just read DX, and DX will be 4001. So what the system is doing is reading 11E, which is 4001. So if we keep looking into the structure, you'll see it there. So 4001 is here, and 202EF. So what it's doing actually is reading the one 4 bytes away from it. Right? Yeah, so it's reading the one. That's the only 4001 I can see unless I missed something. But yeah, so it's reading the block before it, thinking that is the right structure. And there is a really good reason for that, and I'll explain that in a minute, and that will help to understand what's going on. So now if I trace this, and now it will say, is EDX 1005? Obviously not. So if I read the register, DX is 4001. Okay? But I'm going to cheat the system, although it's dangerous to do this, but I'm going to cheat the system to say actually it is. But let's just hack the CPU to say, yes, that register does contain the value. So if I do DX into 1005, and now you can see, oh no, sorry, this should be hex, not decimal, RMDX. Yes, DX is now 1005, as you can see. And now if I pass that a bit, right? So now it's not equal. If it's not equal, it'll jump to this location, but we're in 38, so we're in 40, good. And now it's comparing EAX, which is 2EF, with the 944 it's looking for. And if I cheat the system in exactly the same way, and now you can see I told AAX to be 944, right? And I'm just going to say, yes, it's there. So I just basically, without modifying anything on the code, I just played with the CPU register to say, yes, you are reading the right stuff. You know, what are you talking about? It's all okay. And if I run it now, I'm just going to fire it across and see what happens. There. So now you can see, look, the probe now found 944 vendor, product 1005, version this, probe success. So you see that? And then it will wait for this cycle, current this, error, blah, blah, blah. And now it will have this error, it's not working, and then an emergency stop and blah, blah, blah. So that is the stuff we did stop at on the last video. And today we are going to fix that. Well, I would say 75% fix it, but it'll show what's going on and explain the structures a little bit. But you get the idea now. What happens is the system is coming back with the right information, but because you compile the drivers or the old OS, whatever thing you compile, i.e. the Kronos, on a different configuration or a different operating system or a different hardware altogether, they don't match. This guy is talking English, but the guy wants to read in French. You know, what are you going to do? Anyway, so now that's the gist of it basically. So what I'm just going to do right now is take you through the other system, which is basically will turn into the system. First of all, I need to clear up these breakpoints because I'm going to recompile and then take it from there. So clearing up all the breakpoints and running back again. I need to unload everything in here. Let's load them one by one. So and we're unloading the semaphore and DBG scheduler, FIFOs, scheduler, sorry, yeah, that's fine, and how. For some reason, trying to load one of them, it didn't unload very well. So let's just try to force unload. Minus F. Yeah, it doesn't want to unload, that's fine. It doesn't matter. Right, so now let's just reboot this system. Leave it alone. And I'll take it to the other system that I have. Yeah. And I'll show you on the other side. Let me just get this other. What are you looking at basically when you're doing the system, the OS? We check the stuff, and usually the URB or the OS or the USB is pretty much compiled at runtime, and when it compiled at runtime, all the locations of where things are actually injected on the, during compilation, and because of that, you end up in a system that would look for location 1, 2, 3, 4 for variable X. It's just not going to think about it. It's just going to say, I know X is 1, 2, 3, 4. Pick that up from this location, as you saw on the system. But because we're recompiling the OS, this 1, 2, 3, 4 will change to 5, 6, 7, 8, as I said. And because of that, if I look into the structures in here, so for example, you got the usb-submit-urb on the Kronos, and you got the RH or the Red Hat Enterprise Linux. This is what comes with the OS. So if I look into the function itself of the usb-submit-urb, this is the function that we that I actually picked up initially. That would or that was having problems, at the time. And the issue that you have, you know, when we said the system is actually trying to probe a device, and then the probe is looking for the information, and the information wasn't matching up. That probe was sending back data, but the data wasn't on the original structure, it was actually on the secondary structure. The secondary structure is what the URB is building up. And rather than chasing up the original functions, which are pointless because you have the functions on one side, this, what I mean by that is whatever Korg did, there's no point chasing that up because at the end of the day, they have the information, they have the source code, you have the compiled one on one side, but you haven't got the pre-compiled one on the other side. So rather than wasting time on that, it's easier to pick up an original operating system function and see if you have it on the original and the target machine, and then compare them together and see what the differences are. Or this will tell you, for example, X is reading from 1 to 3, 4 on system A, and X is reading 5 to 7, 8 on system B. Now that requires skills, and you know, you need to know exactly what you're doing before you start working on this. But as I said here, this is the URB structure that I'm looking at. So what I picked up in this system is the usb-submit-urb function, and I also have other functions to look at, but the one we are interested in is pretty much this one. So if I look into the structure of it to begin with, the structure is this, okay? So a URB structure consists of the following. And by the way, it doesn't come with these pointers in here and the sizes. The pointers in here I actually wrote down because I did the calculation myself, and the sizes in here, the same thing. So usually you'd have something like struct, structure, URB, and you got this stuff and then it ends. But this will help me to see where exactly is it in the code and how to work it out. So now KRF, for example, is in location 0 and it's 4 bytes. And for example, SG, without doing any more calculations, SG is in location 48 and is actually 4 bytes as well. So all that stuff is all here, and this will, you know, this will help me to understand. And the reason why I said pick up a function from the OS is because you got the function in here already. This is what Korg sent on the original DVD. And the usb-submit-urb function is nicely, you know, integrated or installed in here for you. You can actually look into it. You can add stuff to it and recompile it again if you like. You can even put printf if you want. But anyway, let's just focus on this. So what we're saying in here on this function, we are picking this up to say if it's not a URB, what that means is if the URB is blank or it's got 0, or the hc-priv. Let's just pick one by one. I don't want to go too fast on this. So I just want to explain what's happening. And let's just pick our system, which is this guy here, and we'll compare it against this guy here. So forget the first part in here. The first part in here will come and say, usually, by the way, AX or EAX in particular, I call it AX because of this, you know, debugger. EAX is what we're looking at. So EAX is the pointer to the structure. So what that means is if EAX is 0, so test EX with EAX is 0 here, then jump, then actually ignore everything else and return to the original caller, which means it is not right. So it'll have error minus EA, which is basically, like we said last time, is 16, error 16. And we'll exit. So just to explain this in slow motion, the system will predict, I think there's going to be an error there. Forget the EBV, ESB, this is different, something else called the stack. And it will here save the variables on the stack and then compare EAX with EAX, and if it's not equal, which means if it's got something, then start looking into the original. So the function starts from here basically. So this part over here, okay, is what it says about if not URB. If URB is something, okay, then carry on. If it's nothing, then return enval. So part 1 of the function is what I just talked about just now. Part 2 of the function is what we come into. Now before we carry on, looking into the Kronos is the same. Well, let's just not look at the Kronos file. Let's just care about Kronos this. So part 2 of the function, now we're sure that the URB has something, but we don't know what it does. It will actually look into the stuff in here to say, you know, read parameter 4, which is the usb-submit-urb, this one I can see there, and that is right, so it's reading usb-submit-urb, right? And it's saying test ESI with ESI. If it is, if it's got something, then fail it, which means usb-submit-urb must be 0. So this is the reserved value, and that is the same thing in here. So fail it means going back to number 18, which is this guy here, and then 18 would do the same exit and bugger off back to the original system. So you get the idea. Just a translation of how this is going into here. I am really good in reading machine code or assembly language like this. Assembly language is this side here. Machine code is on that side. I am really good at understanding machine code by looking at the codes. I can understand it by just reading it sometimes, or I can just disassemble it. Sometimes assemble it just to help me out. But this is what I'm good at. I've always been good at this. So anyway, now I'm not going to go on to the whole function and what it does, because as you can see, it's a big function. We're not care about that. What we really care about in this video is to just put them side by side. So the Red Hat function, or the original one I just compiled from the operating system, or the one sent by Korg, is saying the following, and this is where it gets interesting. So we are reading it from here, and also the other side we are reading it from there. Sorry, yeah, there. All right. So LEA is excluded in here because the jump to 38, not to 32. So 38 is where it starts from. So that definitely LEA has nothing to do with this. So we start from here. Now, here is what the interesting part is. Notice we are reading +4, which is the usb-submit-urb, okay? And I know it says ESI in here, EDI in there, but that's just to do with how I compile the OS. Just ignore that for now. What you need to care about is the EAX bit. So EAX +4, yes, it's the same. So comparing it the same way. So both my OS and their OS are looking at position number 4, thinking it's usb-submit-urb. Great. Now, the other bit is, and this is the interesting part, mine is looking at position 78, which is the complete function, and Korg is looking at it in position 70. And I've noted down in here is actually off by 8. So what that means is I am expecting the complete function to return or to be passed on at location 78, but the Korg compiled system is expecting it at location 70. Now, if you think about it, why would that happen? Can you guess? No, I'm going to wait for you. Anyway, there's two ways that causes this. Either someone from Korg went and said, actually, I'm going to tamper with the system, and I decided to, for example, lift these 3 off from here and then chuck them all in there, and then just scramble this whole thing to make it really hard or impossible for any other guy to actually recompile the system. And which is sometimes a tactic people use to kind of make things lock down the system to only them. What that means is this will prevent people from compiling any further thing to their own OS, prevent them from getting a KO file and then picking up and putting it on a different system to load it up there on a different machine, and ensuring that the system only compiles when Korg or whoever is compiling sends a new update, which is basically what's happening right now. But that could be the reason, is the reason. The second reason is some of the functions or some of these things have been are in a different size to what it should be because of some reason. And the reason for that is when you compile the operating system using the configuration file, it does, you could say to it, I'm not, you know, I want to switch this bit off. I want to switch, for example, power mode or off or on. If you switch the PM on or off, it makes a huge difference to the compilation. I mean, PM on, power management on, will add a lot to some structures and make the system completely different to what you compile, vice versa. The configuration is tons and tons of parameters, and that's why I meant when I said it earlier, I'm actually about 10 steps ahead, because I've done this before and I know what the problem is, and I'm just at the 10th level from now, which is not really worth me talking about it because it's going to bore you up. So so now we have one of three: either a bad structure, you know, kind of tampered with, a bad configuration or different configuration variables, which will be the case, or someone from Korg has really kind of scrambled and copy pasted and played with the structure and moved it around to stop people from compiling. So it might be a good idea. You can do that later on, who knows. But anyway, that's not the point. So if we look into this, in one thing, I mean, just doing the math and the calculation, if I put what I'm actually discovered in here, side by side, I can generate a picture of what happened. So going down the line, so position 20, so position 70 we know is shifted by 8 bits. So let's just do 70 here. That's now gone up by 8 bits, or 8 bytes, sorry, not 8 bits, beg your pardon. Yeah. So now this one has gone up by 8, right? And position 28 is the same. So 28 has not changed. So 28 is, let's say, 0 for the argument's sake. Okay, nothing changed on there, great. So we know up till this point, as the bits I'm highlighting has no shifting, and therefore they're exactly, you know, matching on both systems, which is great news. Now going down the line on this, ignore these two. Let's look into this one here. So position 50 has gone down by 4. Okay, so 54 here is -4. Okay, I worked it out already. I've done the comparison. I know what I've done in the past. I mean, I just went side by side and compared the whole thing. And now 4C also down by 4, which is here, which is 50. Well, 50 minus 4 is 4C, because we're talking hex in here. Anyway, long story short, you can see, you know, things have, that's also on -4 as well. And yep, that's -4 as well. And that was 0 till here. So if I look into this, so the 4's in here, and if I keep going down, 64 has gone down by 8, which is basically 64 plus 8 is 6C. So 6C, where is it gone? Here. So -8. And the others, I mean, I've worked it out already. I picked up a few functions here and there, and I could see clearly, you know, what happened. And that's a -8 as well. And here is a -4. And, you know, etc. So you can now see, as you can look into the structure, as you can see that, the issue we have is, because all that stuff has been shifted by 4, it definitely means someone picked this one here, cut it, right, and moved it somewhere else. Let's just put it there for the argument, for now. If Korg has done that, then looking into this function, it should say, rather than 7C, it should say 80 or something like that, right? But when I've done further debugging, and this is, it actually took me a whole day to actually debug this bit and confirm where the sizes are. So now I'm putting it back, because that hasn't moved, right? The issue we can see, that was a 4-byte and it's to do with the transfer DMA, yeah? And this one is similar, also setup DMA shifted down by 4. So something down the line is telling the system, well, let's just rephrase this. When Korg compiled the system, the DMA, the transfer DMA was 4 bytes with Korg and 8 bytes on my system, which is a problem because now that shifted the whole structure down and caused it to go wrong. And this is the bit that, well, this is the issue that we had in the past, and this is how we fix it. So how to fix the problem, just to confirm all this again. So, you know, you get the idea now. So now we know the transfer DMA and the setup DMA are wrong. So something to do with the DMA addressing is not right. Now I've done the tracing, I've done the debugging, I've done the whole stuff inside out, and I realized when I'd done the compilation on my side, my end, I've actually let me take it to the function anyway. So if I get down to this, I show you here, the file I'm looking at now is the SM types, and you can see it there. So this is the issue that caused the system to fail. And what that is, it says if defined config x64, which we don't have, we're not using 64-bit configuration, right? Or if it's config HiMem64G, which I am using, what I'm doing here in the system is I was thinking, yes, we're not going to use for 64-bit for now, but ideally I'd like to have DMA or have the system addressing in for 64 gig, because someday I'm going to have more memory to give the system and you know, utilize it this way. So that here is probably the issue. What it's saying in here, define it as 64-bit address or define it as 32-bit address. And that says it all, doesn't it? So the DMA address could be a 64-bit or 8 bytes. The DMA address could be 32 bits. So if one of these two guys are up, then it will cause that problem. Now if I go back and telnet into the Kronos, so I'm now connecting to the Kronos from here.
Okay.
I'm videoing, but I haven't got time.
Shall we start then?
Yeah, you guys have fun. Yeah. So now I'm actually on the Kronos now, by the way. So if I'm onto my compilation side of the OS. So use src Linux. And just wanted to show you that before I carry on. So if I grep 4, if I try to look for the config x64 just to see, do I have that? It's not set. So the 64-bit is not set as a whole 64-bit OS. Yes, we know that. But if I try to also grep for the other guy, which is the HiMem64G, and that says Y, and this is where the problem is. So because this is Y, it's causing the problem. So if I go make menu config, okay, now it should come up with a white screen. So now this is the Kronos compilation screen. And if I go down to processor types of features, and if I go down to, where is it gone? Yeah, so memory, we're looking for this guy here. See that high memory support, 64 gig. And I will turn that down to 4 gig. Yeah, so the high memory support. And this is the, yeah, the high memory support is now 4 gig only. So we're now limiting down to a 32-bit address. Okay, so now this is a, well, we can actually have a different thing or have it to off, but this is ideal, the what we'd like to do. So if I save this, so now we saved it, And if I recompile the OS, so let's just recompile it on the Kronos itself, because I don't want to use my laptop for this, because I've got the camera to do that there. Yeah. Right, so let's... let's do this now. So we're going to root. Yeah. Just to show you the same thing I'm just doing now, make menu config, just to show you the thing that we did definitely set it in here. So if I go to processor types and features, and this is this guy, high memory support, and I'm then down to 4 gigabytes. So if I exit, now I'm going to run my rebuild the OS. So from this point, I'm going to skip the video. This is going to take, you can see that here, it's going to take a long time. This will take about an hour or so, but you get the idea now. So we'll leave that now. I'll skip it in a minute, and we'll get back to it soon. In the meantime, I'm going to have my dinner. They're calling me for that. So the other bit is I want to explain what I said about 10 steps ahead. So I'm actually looked into these structures, and I also looked into some other structures in here, and some more structures in there, and some more structures in here. And I'm really close to getting this done. But I think the message is probably after this is now getting to a point where is it worth wasting time doing all this to trying to get this done, or because I know how it works, is it worth me doing some other stuff to make sure that all the drivers work on the new system? The reason I say that, I'm being really careful in here, is one day we need that 64-bit support. So I can twist the system and, you know, beat the crap out of it, and then just to get it to work in exactly the same way. But what's the point? The point is we need something, for example, to say, let's recompile this again. Let's load the new stuff on it to make it work on a 64-bit system, which can have, say, 32 gig memory, not just 3 or 4 gigs there. We can also integrate with other things. We can also probably one day do something like an open source system where everyone can chip in, and we can create a better thing later on. But it's way too early to tell. Doing that stuff is not a 5 minutes job. You probably can appreciate that. It needs a full time. It needs a lot of work and a lot of energy. And the problem I have is I always get pulled up to do something else whilst I'm in the middle of something. And I, you know, mind you, I mean, this whole thing is not paid. I'm doing this because it's something I like to do, not because it's someone paying me to do it. Yeah, I mean, this is basically it. I'm good at what I do. I like doing that sort of stuff. And yeah, so anyway, I'll leave you to it. I'm just going to leave it to compile. I'll speed this up a bit in a minute, and then I'm probably going to speed up one video and keep the other, and we'll just jump onto the other side soon. I'm going to have dinner, and I'll see you in a minute. Right, so now the compilation is finished. Let's see if this is still recording. Yeah, we should be. Good. So now the new thing is now I can see install is all done. The generating of the BZ image and all that kind of stuff is all here. So we now compile the OS, and we're going to. These are the different bootable stuff I actually wrote already now. I wrote a little script to copy the original files into, let's just say YT demo 2, and then we'll do a so this is number 2, and this is 2, that's good. Right, okay. So now we've compiled the system. I just edited the boot up sequence to say, load these files up please. And if I reboot the system now, so the Kronos is going to reboot, and we'll, this is right, I see it here. Okay. Yeah, so YT2 demo, now we're loading this up now. So now we edited the structures. We changed the DMA addressing from 64 to 32 bits. And as a result, the 78 should be 70 now to load up the structure, which has gone by 8. So hopefully we'll see how that's going to go. Oh no, we're doing, yeah, okay. So the HAL, the shared, the FIFOs, the NDBG, the SAM, and also we'll use the, no, we'll just go straight to Omap and KS4. Now, in the past, before I run this, we had a problem of the system finding the wrong device of 4001 and stuff, and we'll see now what happens. Oh no, we need the STG enabler, sorry. So that's STGE. Let's load this again. And there we go. See that? Did you also see the screen is actually flickered? Have you noticed that? So now, look, I'm just going to use this camera to zoom on to things. Yeah, no, it's fine. What's going on is probe found vendor 944, which is what we need, product 1005, version 100, probe success, and we didn't have that before. And then new interface driver, blah, 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 waited that cycles, blah, 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 current, whatever it is, Omap version this, R13, probe, blah. So the NKS is actually reading the Omap version, and it can actually report it down here, which is great. In the read port configuration, line 2, blah, 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 so SW1 is 1, SW2 is 0, so that's the switches are being read to, good. Is 88 key, yes, which is 1, hardware version 0, nil pointer, okay. That is a different error, but the gist of it is, the point of this video is to show you that using debugging techniques is definitely easy to fix. I wouldn't say easy, but it's definitely, for an experienced person, it's easy to fix these issues. And yeah, I mean, I've progressed a lot more than this. I'm now at the CPU registers and the CPU, the task bit as well, whereas tasks are mismatched as well in the same way, so different variables. But you get the idea. I just wanted to take you through this to show you exactly what's going on. Yes, now the driver is loading. Now the system is I'll repeat this again for you so you can see what's going on. This time it does probe it, it does talk to it, it does return back the stuff or the configuration, and you can see the Kronos screen actually flickers when I run the command, which means there is something, there's definitely magic happening in there. It's just, you know, it's not full complete yet, but it's in progress. And again, I'm going to work on other bits and pieces, which will take time. So I probably may not release, you know, a lot of videos on the Kronos soon because I'll be busy doing something else that I really can't talk about right now. You know, and hopefully by the time I'm finished, things will look a lot better than this, you know. But believe me, I'm doing something. You know, I'm working on it. So I just wanted to show you this on that on this on the iPhone. Or actually, I'm going to, you know, use the other camera, so I'm probably going to zoom in using the. This should give you enough space to see. Just to speed things up, I'm going to run my script, which does load up these variables anyway. So they've got all the HAL, the RTI stuff loaded, waiting for me to load up my. So just go down to the bottom there, ins mode, spin, Omap, and caseful. So now, very importantly, keep an eye on the Kronos screen when I run this command, and you'll see how it flickers and it changes things. So right now it says startup failed, power, reconnect, blah, blah. And then if I run this now, watch this. There, something printed here, and the whole thing now changes to white. The progress bar is disconnected and gone grey, and now the red is actually coming up nicely. But there is a little bug down here, as you can see. So I think this is what I wanted to show you, really, a progress of what's going on, and I wanted to kind of take a step back of, you know, just away from what I'm working on now, and I wanted to update you of what's going on. So hopefully you might find my video quite useful. You know, hopefully my head wasn't in the way. It shouldn't be, yeah. So yeah, I mean, I am progressing, and I should have something hopefully later, but it's happening. Thank you very much for your time, and wishing you the best of all. I will do this later on. I'll be working on this now, but I will come up with stuff later on. I do want to do stuff that I really can't talk about. So have a nice day, and thank you for watching.